Welcome everyone, and today we are going to talk about quantum numbers, atomic orbitals, and electron configurations. Understand that quantum numbers are the things that describe atomic orbitals. So, for this, we have to also understand that there are four types of atomic orbitals: S, P, D, and F, which all of them are very weird looking. So, now that we quickly covered about the types of atomic orbitals, let's check some quantum numbers that will describe this. First quantum number is n, which is any positive integer. This is exactly the n value from the Bohr model, the energy level. Let me draw that just to show you. I'm not really good at drawing when it comes to the board, so just bear with me here. Perfect. So this is exactly what the n means. There's another quantum number, which is L. And this is every possible integer, 0, 1, 2, all the way up to n minus 1. And behind, it will be all the way up to negative n minus 1. So we can say that the L value is dependent on the n, because n minus 1 would be the limit here. So if n equals to 3, then L would be negative 2, negative 1, 0, 1, 2, and that's all, because 2 is 3 minus 1. And this is the ones that describe the types of atomic orbital. If L equals to 0, that means that it is an s orbital, which can hold up to 2 electrons. And I won't draw the other orbitals because they're very weird looking, but I'll just draw the p orbital. So when L equals to 1, then we have the p orbital, which are a bit weird looking, but you can think of it as buzz magnets. So these are the p orbitals. Now that we know about L, there's another value of L that we will describe now. There's another quantum number, which is nth of L, which is negative L all the way to L, positive. This is dependent on the L value. This is kind of why there are different possibilities of each type of atomic orbital. If L equals to 0, then nth of L equals to 0, which is why there's only one s orbital, one type. And when L equals to 1, then mth of L would be negative 1, 0, and 1. There is also the spin number, which isn't dependent on anything. It's just, is it a positive spin or a negative spin? So it would be positive 1/2 or negative 1/2. Now that we know about this, We also need to know that this can only be just no electrons can have the same number of all quantum numbers. As we can see from the spin value, at least one has to be positive and at least one has to be negative, as it is shown by the Pauli exclusion principle. There is also Aufbau's principle, which says that what orbitals will an atom take first. First 1s, then 2s, then 2p, then 3s, then 3p, then 3d, then 4s, then 3d, then 4p, then 5p, then 4d, then 5p, then 4f, then 5d, and finally 5f, and so on. That was a long thing. We can see this by energy diagrams. So from this energy diagram, we need to know about Hund's rule, which is that you have to fill the positive spin before the negative spin. So half first, then the other half. So it won't be like this. It will be more like this. That's how we can set things and get an accurate way of doing things. So remember that. Now we can see the number of electrons in chlorine. So at first we can get the first two from 1s orbital, then the other, then on the 2p orbital, remember, first half spin, then the other half spin, then 3s, then 3p. And by all that, we can finally understand that chlorine has 17 electrons. Count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And there's no bottom spin here. So the electron configuration of chlorine would be 1s2, 2s2, 2p6, 3s2, and 3p5. But if we can see the periodic table, we can add a noble gas and write the rest of them as a little abbreviation. So we can write in brackets the neon, which will be said as a neon core. Then we can, and neon has this electron configuration, so we can just write the rest. So this will be the abbreviated version of chlorine's electron configuration. So that's pretty much all there is to it. Please like, comment, and share, and obviously subscribe to my channel. So as always, thank you for watching, and I will see you next time. Bye.